In this video, we're going to take the Laplace transform of hyperbolic sine and hyperbolic cos. Let's start with hyperbolic sine. How are we going to do this? Well, we have to remember that the Laplace transform of any function, so f of t, is given by the integral from 0 to infinity of f of t times e to the minus st dt. This is the formula, the definition of the Laplace transform of a function. So we're just going to plug sine of omega t into the integral. So the Laplace transform of sine of omega t is going to be equal to the integral from 0 to infinity of just that, sine of omega t times e to the minus st dt. Now, hyperbolic sine and hyperbolic cosine have definitions that are in terms of exponential functions, which is going to make this really nice. So sine of omega t, or hyperbolic sine of omega t, is e to the power of omega t minus e to the minus omega t over 2. That is literally what it is. So I'm just going to replace it with that because it's going to make things much easier. Okay, continuing on, we've now got, and I'm going to take the one, what I'm going to do is I'm going to take the 1/2 outside. So I've got a half to the outside, integral from 0 to infinity, and then I'm going to cross multiply, or I'm going to multiply everything out. So I'm going to have e to the omega t times e to the minus st. That's going to be e to the omega t minus st minus, and then I've got e to the minus omega t times e to the minus st. So that's minus omega t minus st dt, just like that. And of course, with a tiny bit more simplifying, we're going to end up with something really, really, really nice. So here, let's factor a t out because that's what we're integrating with respect to. So let's go e to the, and then we're going to have omega minus s t minus e to the, and then what have we got here? Minus omega minus s t dt. And actually, I'm going to do one more thing. I'm going to take a minus to the outside of both of those brackets. This is just a personal preference of mine, but I think it's going to make it easier. So I'm going to do a minus on the outside, which means really I need to have s minus omega in the first one, and then minus e, and then I'm just going to factor the minus out here, so omega plus s t. You'll see why this is nice in just a second. So moving on, we've got a half, and then we can actually do the integral essentially. So what I'm going to do is I'm going to be as formal as I possibly can, because infinity is the limit of integration here, or is one of the limits. So really we should be doing a limit. We shouldn't just plug infinity in. So I'm going to go the limit as, and I'm going to make up a variable x as x approaches infinity. And then I'm actually going to integrate the functions. So the integral of e to the minus s minus omega t is minus 1 over s minus omega times e to the minus s minus omega t. And then the other one, the two minuses will cancel, so plus 1 over omega plus s e to the minus omega plus s t from 0 to x. Okay, so that's why I've introduced the limit, because technically this is a more formal way to deal with an improper integral. Okay, cool. Continuing, we've got 1/2 still on the outside. The limit as x approaches infinity. Big bracket, let's plug x in. So we've got minus 1 over s minus omega e to the power of minus s minus omega x plus 1 over omega plus s e to the minus omega plus s x. And let's put some more brackets around there, minus, and then let's plug in our other values. So now we've got minus 1 over s minus omega times e to the 0, which is the number 1, plus 1 over omega plus s times again e to the 0. Okay, hopefully this makes sense so far. I know it looks a little bit crazy, but we're going to go and simplify it now. So this is a half. The limit as x approaches infinity. And actually, we don't need to keep writing this because I'm now going to take the limit. So let's ignore the limit as x approaches infinity now, because I'm actually going to take the limit in this step. Let's think about what will happen if x goes to infinity. Well, if we have a value of s and omega such that this integral doesn't converge, then we're pretty much at a loss, right? So for example, because we have e to the minus s minus omega times x, we really do need s minus omega to be a positive number so that we are doing e to the minus a number. So e to the power of overall a negative, right? So s minus omega needs to be a positive number. If it's not, we are cooked, okay? And it's just infinite and it's useless. Same thing over here. So if omega plus s is not a positive number, we are, as the kids would say, cooked. So we need both of these to be true. So for a second, just follow me and let's assume that this will converge, okay? If it does converge, as x goes to infinity, we're doing e to the minus infinity, which is 0. So this whole thing here is a big fat 0. And so is this, right? Because same logic, e to the minus infinity is 0. So both of those terms are 0 if it converges. Okay, then we have got a minus minus, so positive, 1 over s minus omega. And then we've got a minus, like a legit minus here, 1 over omega plus s, like that, because the e to the 0 is the number 1. Okay, so I'm going to do a little condition on what omega and s have to be in a second, but let's just get to the end here. So this is equal to 1/2. And then how are we going to deal with this? Well, what we should probably do is give them both the same denominator, right? So I'm going to times the top and the bottom of the first bracket by omega plus s. So I'm going to have omega plus s over s minus omega times omega plus s. And then the second did I say bracket? The second fraction is going to be, we're going to times the top and the bottom by s minus omega. So s minus omega over s minus omega times omega plus s, like that. Okay, and then we can do this all on one line here. So now they have the same denominator. I can add the numerators together. So omega plus s minus minus omega, that's 2 omega. And then we're dividing that by, what's this? Well, if we expand this out, we would have minus omega squared. That's minus omega squared. We'd have plus s squared from the outside terms. And you can probably also see that s times omega, that's just s omega, but then we're doing minus s times omega. So they cancel out. So the entire denominator is just s squared minus omega squared. And then the 1/2 and the 2 cancel. So the final result here is that the Laplace transform of sine of omega t is going to be equal to omega over s squared minus omega squared. Okay, and that's a really nice formula for us. So notice the similarity between this and the typical trig one. So the normal trig Laplace transform, so the Laplace transform of sine of omega t, and I've already got a video on this one, this is equal to omega over s squared plus omega squared. So there's no difference between them except that minus sign in the new one that we've got here. Okay, now I'm not going to do all of the working out for cosh, hyperbolic cosine, because it literally is the same working out, guys. It's the exact same. It's kind of boring. But the Laplace transform of cosh of omega t, and maybe this is an exercise for you that you could try to do the derivation if you want. That's a good idea. But this is going to be s over s squared minus omega squared. Okay, that's the Laplace transform of cosh of omega t. And again, we can kind of compare that to the Laplace transform of just cosine or cos of omega t. That is s over s squared plus omega squared, as you might guess, right? The way that I remember these, by the way, guys, is sine starts with an s and it doesn't have an s on the numerator. Cos doesn't start with an s and it does have an s on the numerator. So it's like the other way around. So it would be kind of nice if it was like sine had the s on top and cos didn't, but I always remember as it's the other way around to that. So I know that sine has the constant on top, not the s, and cos has the s on top, not the constant. And it's the exact same thing with the hyperbolics as well. Now, earlier I said we're going to make a very bold assumption up here. If we navigate back up to the working out, we could only go from this line to this line if something very, very specific was the case. We needed s minus omega to be a positive number, and omega plus s needed to be a positive number as well, because those are in the powers and there's already a minus sign on the outside. So they needed to be positive. Okay, now typically s is a complex number and omega is going to be a real number. Okay, so if we if we think about rearranging this a little bit, we can say that s has to be bigger than omega, but also s has to be bigger than minus omega. Okay, so really what that means is that the modulus of omega needs to be less than s. But again, s can be a imaginary or a complex number, so omega just has to be less than the real component of s. Okay, now typically for most people using Laplace transforms, this doesn't really matter very much. So don't worry too much about the pedantics of what the number omega actually has to be with respect to this new variable s. It's only if you're really specific, and there can be situations where you need this, but it's very, very rare. It's quite few and far between. So if you're curious when this integral converges, it's in this situation, when the magnitude or modulus of omega is less than the real component of s. So that will guarantee that the integral converges and we can actually access these results. But that is the Laplace transform of the hyperbolic sine and the hyperbolic cosine functions. Thank you so much for watching. As always, I highly appreciate it, guys. You know that. And I'll see you in the next one. Cheers.